And if we take a look at a lot of the devices that you may have in your hand right now, or the one sitting on your lap if you happen to be watching this video here, many of our devices today use some sort of stored electrical energy, and it's quickly becoming one of the more common types of energy storage today. Primarily, we are storing our energy in the form of batteries, but there are some other ways that we can store energy as well. We're just going to focus on what you might see in batteries, and later in the chapter, we'll actually start looking at things that you might see in fuel cells. Now, electrochemical reactions involve the transfer of electrons from one substance to another, and we are able to harness the electrons being transferred and route them through a circuit that we create, and that's how we get our electricity. Now, the reactions that create these electrons in this transfer are called redox reactions, sometimes also occasionally called electron transfer reactions. We've seen these in Chemistry 141 back in Chapter 9, but let's go ahead and review just a couple of the more base concepts from that chapter. So one of the concepts that you learned in Chemistry 141 is this idea of oxidation numbers. And really the easiest way to be able to identify a redox reactions is to assign oxidation numbers to all the elements present in a reaction, and then see if any of those oxidation numbers change for any given element in going from reactants to products. So if we take a look at this reaction here, magnesium metal plus 2HCl goes to MgCl2 plus H2. And if we assign oxidation numbers to everything here, what we would see is magnesium in its elemental state would have an oxidation state of 0. The hydrogen in HCl would have a +1. The chloride would have a -1. The magnesium in magnesium chloride would have a +2 oxidation state. The chlorine would still have a -1. And the hydrogen here in its elemental state would have a 0. So we see that magnesium changed oxidation states going from 0 to +2, and the hydrogen changed an oxidation state going from +1 to 0. So what we saw there is that the magnesium lost 2 electrons, and any time an element loses 2 electrons in going from reactants to products, we say that that element is oxidized. The hydrogens we saw gained an electron because they went from a +1 oxidation state to a 0 oxidation state. So when elements gain electrons, we say that they are reduced. We can remember gaining, losing, oxidation, reduction with a couple of different acronyms here. We can use OIL-RIG, which stands for oxidation is loss, and reduction is gain, or Leo goes grr. We have loss of electrons is oxidation, gain of electrons is reduction. So again, these concepts should be review for you, and if you're not terribly comfortable with them, I certainly encourage you to go back to Chapter 9 in your text and review that section. Now, anytime we have oxidation and reduction happening, those processes have to occur as a pair. We cannot have just oxidation or just reduction. If something is losing electrons during the course of a reaction, something else must pick them up, and vice versa. So we always have oxidation and reduction occurring at the same time, which is why we call these reactions redox. Now, anytime we have that redox reaction, we can split the overall reaction into half reactions. We can have an oxidation half reaction and a reduction half reaction. Let's take a look at an example. So here we have the reaction of zinc plus copper 2+, so zinc in a copper ion solution, going to zinc 2+ plus copper metal. Now if we assign oxidation states here, what we would find is that the zinc is losing 2 electrons, going from zinc to zinc 2+. So that would be our oxidation half reaction. We also see that copper is gaining 2 electrons, going from copper 2+ to copper. So that would be our reduction half reaction. And we're going to write them like this. We have zinc going to zinc 2+ plus 2 electrons. Anytime we're writing our half reactions, we have to make sure that we remember to put in electrons in the appropriate side. Oxidation half reactions have electrons as products. Reduction half reactions have them as reactants. So here we have copper plus 2 electrons going to copper metal. So we have copper 2 plus 2 electrons going to Cu. So we have both our oxidation half reaction and our reduction half reaction. We use those half reactions in order to balance redox reactions. Now the reason that oxidation reduction reactions have to be balanced is because we have to balance mass. We have to account for all of the atoms and also all of the electrons. And so we also have to balance charge. That's the easiest way to account for electrons. We balance mass primarily by making sure we have the same number of each atom of an element in products and reactants. And in order to balance electrons, we also have to balance total charge in the reactants and the products as well. Let's take a look at an example of a reaction that looks balanced, but in fact is not. When we look at this reaction, iron 3 plus aluminum goes to iron 2 plus aluminum 3 plus. Initially, it may look like it's balanced because we have one iron in the reactants, one iron in the products, one aluminum in the reactants, and one aluminum in the products. So that would appear balanced by all of the balancing measures we've applied so far in our classes. However, if we were to count electrons, we would see that there are some electrons missing from the reactant side. So this reaction is not balanced. We could also see that by looking at the charge. The charge in the reactant side has a total of 3 plus, and the total charge on the product side is 5 plus. We have 2 plus on the iron and 3 plus on the aluminum. So let's take a look at a method of how we could balance redox reactions. The easiest way to balance redox reactions is to use what's called the half reaction method. This has some steps, and then we're going to expand this a little bit more. So our initial method, first thing we're going to do is to write the reaction in half reaction form. So that reaction, we had iron 3 plus going to iron 2 plus. That's our reduction half reaction. And aluminum going to aluminum 3 plus. That's our oxidation half reaction. Next, we're going to balance any elements other than oxygen or hydrogen. Well, this reaction does not involve doing that because we have one iron on both sides and one aluminum on both sides. So we're already balanced as far as the elements. Next, we want to balance the charges on each side using electrons. We see for the iron that we need one additional electron in the reactants to make sure that the charges are exactly the same. The negative one from an electron plus a 3 plus brings us to 2 plus that we have in the products. For aluminum, I have no charge on the left and a 3 plus charge on the right. So in order to balance that out, I'm going to add electrons, and I have to do it to the more positive side. So that would be on the product side. Whenever you're balancing your electrons, you should always have electrons on one side for one of your half reactions, and on the other side for the other half reaction. You should never have electrons on the same side for both of your half reactions. So now we're going to multiply the two half reactions by a factor so that they both have the same number of electrons. So we saw that the iron half reaction has just had one electron. The aluminum half reaction has 3 electrons. So we're looking for a lowest common multiple. So our lowest common multiple here is going to be 3. So I'm going to want 3 electrons in both both sets of half reactions. So I need to multiply the reduction half reaction by 3, the oxidation half reaction just by 1. That will give me 3 electrons on both sides. Then I'm going to add the two half reactions together, canceling anything that shows up on both sides. This should always be your electrons. It may be some other things as well, but always your electrons. So here we see we have 3 electrons plus 3 irons goes to 3 iron 2 pluses. And we have aluminum goes to aluminum 3 plus 3 electrons. We add that up, and we see that our electrons cancel, and we're left with 3 iron 3 plus aluminum goes to 3 iron 2 plus aluminum 3 plus. We see that our total charges cancel out. We have a total of 9 pluses here in the reactants. In the products we have 6 pluses plus 3 pluses or 9 pluses as well in the products. So my elements balance and my charges balance as well. So that means I have a balanced redox reaction. Well, let's look at a reaction that's a little bit more complex. Many of our redox reactions take place in aqueous solutions, and many of those aqueous solutions are either acidic or basic. And when that's the case, the presence of H+, H2O, or OH must be accounted for, because very frequently those species are taking place in a redox reaction. So what we need is a way to balance the oxygens in any water or any oxoanions that are part of the redox reaction. We're going to use a method that is very similar to what we just performed with the aluminum iron example, but there are a couple of extra steps that we have to throw in order to balance hydrogens and oxygens. Our first example is going to be balancing a redox reaction that's taking place in an acidic environment. Then we'll do a basic environment after this as well. So the first thing we need to do is to write the unbalanced net ionic reaction. So we have Fe2 plus a dichromate ion goes to iron 3 plus chromium 3 plus. Next step is we're going to separate that reaction into two half reactions. Normally you can figure out which half reactions you're going to have to do by making sure you have similar elements in both of the half reactions. The oxygens will balance in a later step. But when we separate this reaction into half reactions, notice that I have irons only in the oxidation, and I have all my chromiums in the reduction. So all my irons are in one step, and all my chromiums are in another step. So that's probably the easiest way to separate half reactions. So I have my oxidation half reaction. I have iron 2 plus going to iron 3 plus. I have my reduction half reaction, the dichromate 2 minus going to chromium 3 plus. It isn't terribly important that you know which of these is oxidation and which is reduction when you're doing this method. It doesn't depend on you knowing which is oxidation and reduction. But you should be able to figure it out if that question is asked. Well, once you've separated the reaction into half reactions, next thing you want to do is balance any elements other than oxygen or hydrogen. So we're going to take our iron, 2 plus goes to iron 3 plus. That's already balanced. We don't have to do anything there. For our reduction half reaction, notice that we have 2 chromium atoms on the reactant side, but only 1 on the product side. So we have to balance the chromiums, and we do that by adding a 2 in front of the chromium 3 plus. So now every element other than oxygen or hydrogen are balanced. Now we want to balance our oxygens and hydrogens. So we're going to add water to whichever side we need in order to balance oxygen atoms in each half reaction. And then after adding water, we'll add H pluses in order to balance any of the hydrogens that are out of balance. So once again we see our iron with no oxygens, it doesn't need any water. Our second step, however, does need to add some oxygen there. We see we have 7 oxygens in the dichromate ion, and there's no oxygens in the chromium ion. So I need to add 7 waters on the product side there. And then the next part is to add H pluses to balance the H's. Well, I have 14 hydrogens now from the water in the product side, and there's no hydrogens on the reactant side. So I need to add 14 H pluses in the reactant side for the bottom half reaction. The next step is to balance the charges on each side using electrons. So I have a 2 plus on my iron reactant side and a 3 plus on my iron product side. So I need to add an electron to the reactants there to make sure that we have 2 plus in the reactants and 2 total pluses in the products. My chromium's a little more complicated, but it's really no different. We just have to add up all of the charges. I have 14 pluses and a 2 minus in the reactant side, so that's 12 total pluses. And then on the product side, I have 6 total pluses. So I have 12 pluses in the reactants, 6 pluses in the products. I have to get rid of some of those pluses, and I do so by counteracting them with minuses. So I need 6 electrons to be added to the reactant side of the bottom half reaction in order to balance out the charges. Now I need to multiply the two half reactions by some factor so that they have the same number of electrons. I've got a lowest common multiple of 6 here because I have 6 electrons in the bottom, 1 electron in the top. So I'm going to multiply the top reaction by 6 and the bottom reaction just by 1. So that gives me 6 iron 2 pluses, 6 iron 3 pluses, and 6 electrons. Then I'll add any of the two reactions together, canceling anything that shows up on both sides. Your electrons should always cancel, and sometimes you'll get some other things canceling, particularly any of the H pluses or the waters. We don't have that situation here, and we end up with our electrons canceling, and we get 14H plus Cr2O7 2 minus plus 6Fe 2 plus goes to 6Fe3 plus 2 Cr3 plus 7 waters. You always want to go back through, verify that all of the atoms and all of the total charges balance out. Let's take a look at balancing a reaction in base. There are various methods for balancing a redox reaction in base. However, I prefer the method that's presented in the text. First thing we want to do is complete the balance of the reaction as if it were an acid. Even if it is in a basic solution, we're going to balance the reaction as if it were an acid, and then we're going to make some adjustments. So after you've balanced the reaction in acid, then what we're going to do is we're going to add OH minus ions, so hydroxide ions, to both sides of the reaction to neutralize any hydrogen ions that are on one side of that reaction. And we're always going to add the exact same number of hydroxide ions to both sides. Once we've completed the balance of the reaction in acid, it is a balanced reaction. So any adjustments that we make by adding or removing something, we want to do the same thing to both sides, and that will keep our reaction balanced. So once we've added hydroxide ions, we're going to combine any H plus and hydroxide ions to form water, and then we take a look to see if there's water on both sides of the equation, cancel out any common H2O pluses, and get a result for a final balanced reaction. It sounds more complicated than it is. Let's go ahead and do an example. So we're going to take the reaction that we just did and assume that instead of being an acid, that we're going to balance it in base. We still would have reached the same point having balanced it in acid, but now we're going to be changing the reaction to be in base. So this is where we finished after we balanced the reaction in acid. So now we're going to add our additional steps for balancing it in base. We see that we've got 14H pluses in the reactant side, which means I need to add 14 hydroxide ions in order to neutralize that H plus. I'm going to add hydroxide to both sides to neutralize the hydrogen ions that are on the reactant side. So we get this. We have 14OH minus plus 14H plus. And then we have the 14OH minuses in the product as well. We're going to simplify the 14OH minuses and 14H pluses and turn them into 14 waters. So we're going to simplify the hydroxide and H plus into water, and then we're going to cancel because that will give us waters on both sides. So now we have 14 waters in the reactants, and we still have the 14 OHs in the products. We don't mess with those. There's nothing to add to them to make waters. But notice that we've got 14 waters on the left, and 7 waters on the right. So we're going to cancel out the 14 and the 7. So the 7 waters go away completely from the product side, and 7 waters are still left in the reactant side. And so this is our final balanced reaction in base. As I said, the steps sound harder than they are, but once you actually put them in practice, they're really not too bad. Well, here's an example that we're going to do in class. If you get the chance, you might try to work it out on your own, but we will finish out class with this example. And we're going to start off talking about galvanic cells. Now, a lot of times when we have a oxidation reduction reaction, it happens when a reducing agent is in direct contact with an oxidizing agent. And when that happens, the electrons that are transferred in the reaction can be transferred directly between the two materials. Now, in the example we saw earlier between the copper and the zinc, we saw that the copper was the oxidizing agent. It caused the zinc to be oxidized, and that was in contact with the zinc metal, which caused the copper ion to be reduced. So that was the reducing agent. So galvanic cells are spontaneous electrochemical reactions where the electrons flow once that circuit is complete or once the materials come in direct contact with each other. Now, a lot of times what we want to do is we want to be able to separate these components and allow the electrons to transfer through an external circuit, something conductive, such as a wire. And we'll be talking a little bit about those a little bit later. Let's talk a little bit more about these galvanic cells. Now, sometimes they're also called Voltaic cells. You'll see both names. The key with either a voltaic or galvanic term is it means that that cell moves electrons spontaneously. So it's an important term. We do not have to apply electrical energy to continue that electrochemical reaction there. So as we just mentioned in that previous slide, one of the things that we can do with our half reactions is to separate them physically and not allow them to come into physical contact with each other. And we can, however, make them contact each other through an external circuit, so something through like a wire or something similar. Now, once that circuit is completed, the spontaneous electrochemical reaction will begin, and those electrons will in fact flow from one side of this, one cell to the other cell. And let's take a look at a picture of what that might look like. So here's a voltaic cell. We've got several parts and pieces here. We've got two materials. We've got a copper electrode and a zinc electrode. The zinc electrode is in a zinc solution in a beaker, and that copper electrode is in a copper solution in the beaker. We've got alligator clips connecting those electrodes. We see electrons flowing through the wire, and we have electricity flowing and lighting up that light bulb there. Now, we see here that we've got oxidation happening here with the copper, and anytime you have oxidation taking place in an electrode, that is going to be your anode. Conversely, anywhere that you have reduction taking place in a galvanic cell, that is going to be your cathode. Now, part of what makes that important is that your anode and cathode have very specific signs. Your anode is always going to be the negative pole of your battery. Your cathode is always going to be the positive pole of your battery. And we also have this thing in the middle called the salt bridge. Now, if we look here in our oxidation half cell, we're going from zinc solid, our electrode there, and it's becoming zinc 2+. So we're putting zinc, positively charged zinc ions into the zinc solution there. And we have to maintain a balance of plus and minus. So in order to maintain charge neutrality, we have nitrate ions coming out of that salt bridge going into that solution. So you have positive ions coming off of the anode and nitrate ions coming out of the salt bridge in order to neutralize that charge. On the other side, we've got a reduction reaction. So we've got copper 2+ ions turning into copper metal. So we're actually removing positively charged ions, and again we have to maintain charge neutrality. So from the salt bridge, the cation out of the salt bridge is going to be coming in here to replace the positive ions, positive copper ions that have been reduced. So there's a lot of things that we can tell just by knowing the materials in a voltaic cell. One of the other things that we can look at is the direction of electron flow, and electrons always will be flowing out of the anode. So here they're going this way and into the cathode. And the way I always remember that is that you have electrons moving away from the negative. They're being repelled by the negative, and they're being attracted to the positive because of those opposites attract and likes repel. So let's talk a little bit more detail about that salt bridge. It really does play a very important role in electrochemistry. The key thing that it does is it completes that circuit between the two half cells, and without it the battery would simply not work. So it provides a constant flow of charge. So we can try, if you go back to that previous slide, you could look at how negative charge comes up out of the electrode across the wire to the right down into the cathode, and then the negative charge on the or in the salt bridge continues on moving around to the left, and so you have a constant loop of negative charge there. And as we just talked about, its most important role is to balance the charges in those solutions and allow that battery to continue to run. So here's an example of a cell. We have iron solid plus copper ion going to iron ion plus copper metal. And we'll work this one out in class. We're just going to sketch a picture and show where our anode, cathode is, oxidation and reduction, plus minus poles, direction of electron flow, and direction of ion flow from the salt bridge. Well, as we'll see in class, every time we want to write out a cell, drawing a cell in order to refer to a particular electrochemical reaction can be a little bit tedious, having to draw the half cells, draw the salt bridge, draw the electrodes. We don't want to have to do that every time we want to indicate an electrochemical reaction there. So we have what's called cell notation that describes the exact same cell as one of our cell diagrams that we just drew out. Let's take a look at that cell again, our copper zinc cell, and we can write it in cell notation so that it looks something like this. Well, let's take a look at all the different parts and pieces to this cryptic looking notation here. So we see our zinc and our copper there. We don't put them in just any order. There's very specific orders in how we write this. So on the left hand side, we always write our anode. So, and we write our electrode there first, so our zinc, and then we have our solution that's separated by a single line. On the right hand side we have our cathode, so we have our copper solution there and our copper metal on the outside. So we always put our electrodes on the outer edges of the cell notation. The single lines that we have there are our phase boundaries. So that's the phase boundary between the solid copper or zinc and the solutions in which we have those. That double line in the middle is our salt bridge that physically separates the copper half cell from the zinc half cell. Well, here's another example that we'll work out, and we're going to write this particular example out in cell notation. Now occasionally, when we're doing an electrochemical reaction, one of the electrodes used in the cell may be a gas, or it may be an already ionized species. So it may be like an iron 2+ being oxidized to an iron 3+. That's a very common reaction as well. So we don't have a solid species to act as either the anode or the cathode, or if it's a gas, trying to hook an alligator clip up to a bubble of gas is quite difficult as well. So what we really need is an electrode that can bring the electrons or take the electrons to or from the desired reactant, but not get involved with the reaction itself. We don't want to introduce a material that will change the electrochemical reaction that we're interested in. Now, one of the more common materials that we use to do this is platinum. So we do have platinum electrodes, and occasionally gold or mercury are used as well. Now, the reason we would use these metals is that electrochemically they're very unreactive. They're extremely stable in electrochemical environments, and so we use them very commonly in order to react either with a gas or with an ion, but not react themselves. They just become a conduit for electrons moving one way or the other. Another common electrode that's similar to this is what's called a standard hydrogen electrode, or an SHE. And the reason it's so common is that we use it as a voltage reference for virtually every chemical reaction that we see. So here's an example or a diagram of a standard hydrogen electrode. We've got gas, hydrogen gas flowing in here at 1 atmosphere, and it will fill this test tube. This is sealed up in here, so gas can't escape up in that area, but it fills this complete test tube and it puts it in contact with this platinum electrode down here, and then we've got the H plus down there. So we've got a source of the gas, the reduced species, and then we've also got a source of the oxidized species down there with the H plus. So this is very similar to just putting like a piece of zinc in a zinc solution or a piece of copper in copper solution. This is just putting hydrogen bubbles into a hydrogen ion solution. And so this is a standard hydrogen electrode. Now, anytime we're doing these reactions here, particularly with galvanic cells, we're moving electrons through a wire. Well, anytime something is moving, there must be work that gets done to move those particles. And we can always think of electricity moving through a wire, kind of like water moving through a pipe. And it's always going to move from a higher pressure to a lower pressure. Now, what is causing this pressure in an electrical circuit? Well, it turns out it's potential energy. There's a potential energy difference in the materials used for the different electrodes. And we measure this potential difference in the unit of volts, which is why when we talk batteries, we're always talking about volts. Even when we go to the store and buy our regular AA batteries, they're 1.5 volts. Now, 1 volt is the amount of energy needed to impart 1 joule of energy to an electric charge of 1 coulomb. And just for some more definitions here, the amount of charge contained in 1 mole of electrons is 96,500 coulombs approximately. It's actually slightly less than that. But this is called a Faraday of charge. And we'll start using Faradays and coulombs a little bit later in the chapter. Let's go back to this idea of electromotive force. There's a lot of different factors that can change the voltage coming from a cell, and so in order to tabulate these values, we want to have a set of conditions that we can use to measure standard potentials. And so we get an idea of what's going on in a battery without having to worry about the absolute conditions. We can use standard potentials, and these have a set of conditions that we already know about. And so these standard potentials always have reactants in products in their standard states. If any of the aqueous solutions, so for example the copper or zinc solutions that we saw earlier, those would be at 1 molar concentration. If there's any gaseous substances, they're going to have a pressure of either 1 bar or 1 atmosphere. They're both pretty close to each other. The temperature is 298 Kelvin. And the cell potential measured under these conditions give us a standard E for the cell. So we use E to indicate voltage or electromotive force. Cell for a particular cell, and the little 0 there indicates that we are under standard conditions. So how do we find our E0 cell for a battery? Well, if we look at each of our half cells, what we'd see is that each electrode and its half cell has its own potential as measured against a standard hydrogen electrode. Now we have to set something as 0 so that we can compare each half cell's potential against something else. And so we compare it against a standard hydrogen electrode, and we set that at 0 volts. Now some electrodes will be higher than the standard hydrogen electrode. They'll have a higher reduction potential, and so those will be positive voltages in our table, and some of our half cells will have a lower reduction potential than hydrogen, and those will have a negative potential compared to hydrogen. And so we tabulate these values again as reduction potentials, and we write all of our reactions as reduction reactions. So we can calculate our E0 cell from the 2 half reactions, the oxidation half reaction and the reduction half reaction. And we can do oxidation potential plus reduction potential for our 2 half cells and get our E cell. Now when we write a redox reaction, obviously we're going to have both of those 2 reactions occurring, so we'll have both a reduction and an oxidation reaction. Now we just mentioned that all of our values are tabulated as reduction potentials, but we can still find the oxidation potential of a reaction. We just look up that reaction's reduction potential and reduction reaction, and the oxidation reaction would just be that reduction reaction written in reverse. And since we write it in reverse, we would just change the sign of the reduction potential, and that would give us the oxidation potential. So another equation that we can use to find E0 cell is if we can identify the cathode and the anode, we can use just reduction potentials that are listed in the table and say that the E0 cell is equal to the reduction potential of the cathode minus the reduction potential of the anode. And this way we don't have to identify what's being oxidized, what's being reduced. We don't have to worry about which sign we're going to change in the potentials. Now E0 cell is an intensive property of a cell, so the amount of material that we use in the electrodes does not affect the voltage. It doesn't matter if we use a gram in an electrode material or a pound in an electrode material. Both of those electrodes are going to give us the exact same voltage. Well, here's a reaction or an example that we'll do in class. No, sorry, we're actually going to do it here. We're going to look at the reaction between copper and zinc. And so here we're given the reaction between copper and zinc. We have copper 2 plus zinc metal, and that's going to go to zinc 2 plus copper. And all of these solutions are 1 molar to indicate that we're under standard conditions. Now in our table here, we see that copper plus 2 electrons gives us copper metal, and that has a reduction potential of 0.34 volts. And the zinc reduction potential is at negative 0.76 volts. So we see that copper is the stronger, or copper 2 plus is the stronger reducing agent. Take that back, the stronger oxidizing agent. And so that means that copper 2 plus will be reduced and is going to represent the cathode in our reaction. And we see that from our net reaction anyways, because we see we have copper 2 plus going to copper metal. And that indicates a reduction reaction. So that means that the zinc going to zinc 2 plus is going to represent the oxidation half reaction. So what we see from the reaction is that copper is a reduction, so that's going to be our cathode. We write that first, minus the reduction potential for the anode, the zinc, and we get our E cell of 0.34 minus a negative 0.76, and we get a total voltage of 1.10 volts. So now we have our table of reduction potentials. We can look at just the materials used in a battery and figure out a whole lot of things about that battery. And if we make a battery out of aluminum and nickel and their solutions, these are the things that we should be able to find. We should be able to find the cathode, the anode, the oxidizing agent, the reducing agent, the overall reaction, the direction of electron flow, the number of electrons transferred, and the overall cell voltage. So this is an example that we did work out in class using aluminum, nickel, and their solutions. Well, anytime that we use our reduction potential and we place the cathode with the material that has the higher reduction potential, we're going to get a spontaneous battery because we're going to have a positive E cell. We also know that any reaction that has a negative delta G is also spontaneous. So we've used that word twice now, a positive E cell being spontaneous and a negative delta G spontaneous. So there must be some link between the two, since both of them represent a spontaneous reaction. As it turns out, there is a link. Those two quantities are linked by work. And your book goes through a derivation of how to get to this next equation, and if you choose to take a look at that, I certainly invite you to. It is not something that we'll cover in class. It's not something that I'm going to test you on. But here's our equation that relates delta G and our E cell. So if we have non-standard conditions, we can just do delta G is equal to negative N Fe, or if we have standard conditions, we can do delta G0 is equal to negative N Fe0. And our values in there, so N is the number of electrons that are transferred during the course of a reaction. F is Faraday's constant, which is basically 96,485 coulombs per mole. And E, of course, would be the E cell that we calculate using the method we just learned. As it turns out,
we can also link electrochemistry and equilibrium. Since we've seen now that we can link E cell and delta G, and we've seen earlier that delta G links to K, there must be a link between E cell and K. So we've already seen that. We have that relationship between delta G and K. So if we take the value, or the equation that we just learned for delta G0, and replace it with negative NF E cell, we end up with an equation that says E0 cell is equal to RT over NF natural log of K. Now R is our gas constant, 8.314 joules per mole Kelvin. T is temperature in Kelvin. F is Faraday's constant. And N is the number of electrons transferred. Well, if we're under standard conditions, then we're at 298 K, and R, T, and F become constants. So we can just lump those together and calculate their values and plug them into the equation and get E0 cell is equal to 0.0257 volts over N natural log of K. Or if you prefer to use the common log, you can say 0.0592 volts over N log of K. Both of those equations are equivalent. You don't have to worry about what situation you use one in or the other. It just depends on whether you prefer to use the natural log or the common log. And here's a reaction that will work out in class. So where does all this take us as far as the relationships between delta G, K, E cell, and the reaction position? Well, if we look at a value of delta G being negative, we know that that means the reaction is spontaneous. That means that that K for that reaction is going to be greater than 1. E cell is going to be positive, and the reaction position is going to favor products. If we have a delta G that's 0, K is going to be equal to 1, E cell will be equal to 0, and the reaction position means that that reaction will be at equilibrium. And if we have a positive delta G, that means that K will be less than 1, our E cell will be negative, and the reaction position there favors the reactants. And here's just a summary of how E cell, delta G, and K are all linked together. They all have an equation. They're all derived from each other. Let's look at non-standard cells now. We've talked quite a bit about standard cells where you have E0 cell, but most electrochemical cells operate under non-standard conditions. And if you think about it, if you started with a standard cell where your solutions were at 1 molar, as soon as that cell begins to operate, the cell becomes non-standard because the concentrations of the solutions within the cell are going to start to change. So it's good to be able to calculate voltages for cells that are under non-standard conditions. In particular, concentrations and temperature can change for a non-standard cell. Well, the equation that we use to calculate the voltages for non-standard cells is called the Nernst equation. It uses temperature and the value of Q to determine how far away the voltage of our non-standard cell is from that of a standard cell. The equation looks extremely similar to what we found for delta G. If you remember, we had delta G is equal to delta G0 minus natural log of Q, and here we've got E cell is equal to E0 cell minus RT over NF natural log of Q. So a very similar equation. We can look at our constants here. We have our R at 8.314 joules per Kelvin mole. Our Faradays are 96,485 coulombs per mole. N is the number of electrons transferred in the balanced reaction, and T is in Kelvin. And Q, of course, is our regular Q, products over reactants, and we use coefficients from the balanced reaction as our exponents. So this equation has a couple of different forms, either of which you can use. If we're at 298 K, again we run into a similar situation for what we found earlier. We have N, F, and T, R, T, and F that we can plug in as constants. And if we use the natural log of Q, we get a value of 0.0257 in that numerator for our fraction. Or we can use the log version, the common log version, and get 0.0592. Again, we use this if the reaction is at 298 K. If it's at a different temperature, then you need to go in, calculate the value of R, T, and F, and plug that into the equation. Well, here's an example of our nickel aluminum battery. We've got non-standard battery here. We've got our aluminum concentration at 0.001. and our nickel concentration at 0.5. Remember, under standard conditions, both of those would be at 1 molar. Here they're clearly not at 1 molar, so it's going to change the voltage. Now if we look at our reduction table, we see that nickel is higher on the table, so it will get the electrons, which means it will be reduced. It will be the cathode. So at our anode, we have oxidation taking place of the aluminum. So we have aluminum going to aluminum 3 plus 3 electrons, and we've got our reduction potential there. At the cathode, we've got nickel 2 plus 2 electrons going to nickel metal, and that has an E0 of minus 0.25. Now I've got to add these two reactions together, and I've got to do it in a way that the two electrons on either side of the arrow will cancel. So I've got 3 electrons in the top and 2 electrons in the bottom. My lowest common multiple is 6, so I need to multiply the top reaction by 2 and the bottom reaction by 3 to get 6 electrons and get those to cancel. When we add those up after that, we're going to get 2 aluminums plus 3 nickel 2 pluses going to 3 nickel solids plus 2 aluminum 3 pluses. Our E cell here is going to be plus 1.41. Notice something that's a little bit different from what we've been doing in thermodynamics. Then our E0 did not get multiplied when we multiplied the anode and cathode reactions by 2 and 3. Okay, remember that E0 is an intensive property, and this means that the amount of material does not alter the E cell, and it's no different for our half cells. So we never multiply that E0 value by the value that we multiply the half reaction by to get the electrons to cancel. We just use the tabulated values, and we don't manipulate them in any way. So now we know our E0 cell under standard conditions at 1.41 volts, and we know that N is equal to 6 because that was that lowest common multiple for the number of electrons transferred on both sides. Our Q is going to be products over reactants. Our product ion was aluminum 3 plus, and that's going to get squared because it had a coefficient of 2. Our reactant ion was nickel 2 plus, and that gets cubed because there is a coefficient of 3. We still don't include any of our solids, so the nickel metal for the products is not included, and the aluminum metal for the reactants is not included because they're solids. So now we can plug everything in. We have our E cell is equal to 1.41 minus 0.0257 over 6 times the natural log of 0.0010 squared over 0.5 cubed. And we work out some math there, and where we end up with is an E cell at 1.46 volts. So our E cell is just slightly higher under these conditions than they are under standard conditions. And if we look at our reactions here, or our concentrations for our solutions, that makes sense. Under standard conditions, we have 1 molar aluminum and 1 molar nickel. Here we see that we have a much greater concentration of nickel than we do aluminum, which means we have more ion in the in the reactant than we do in the product. So the reaction is even farther away from equilibrium. So there's a greater push to move from reactants to products in order to reach equilibrium. So the voltage is just slightly higher at this point.
So the first thing we're going to talk about today is just a little bit of an extension on the Nernst equation, and this has to do with things that are called concentration cells. And these are galvanic reactions that occur even when the metals in the two half cells are exactly the same. Normally, if we had two metals that are the same, we would expect there to be no difference in potential energy, so we would expect there to be no flow of electrons from one metal to the other, since the two metals have the exact same potential. However, there is a driving force that can come if the concentration of the solutions that the metals are in, that the electrodes are in, are different, and that does provide a driving force to move the electrons from one half cell to the other. And the electrons will flow from the half cell that has a lower ion concentration to one of higher concentration. So we will have oxidation occurring in the half cell with a lower ion concentration, because that will increase ion concentration, and they will flow to the side that has a higher ion concentration in the solution, because reduction will occur there, and that will remove ions from that solution, and so that will decrease the ion concentration in that cell. And so the driving force is trying to get those concentrations in the solutions to be the same, and once that happens, then we'll have a dead battery. But even though we have the same metals, we can actually get electrons flowing from a lower concentration to a higher concentration, even with the exact same metal. So we can take a look to see what that looks like here. And here we see standard conditions for a cell. If we had a 1 molar copper solution in both of these here, we would see that there is no net electron flow, and we have a voltage of 0 there. But on this other side here on the right, we see that we've got a 2 molar solution on the right hand half cell and a 0.01 concentration on the left hand half cell. And so the electrons are going to be moving out of the anode here, going this way, flowing through the voltmeter and down here. And what that means is that we're going to get reduction taking place. So the concentration of copper in the solution here on the right is going to go down because we're making copper out of copper ion. And then here we're going to have copper ion concentration going up because we're going to have oxidation. We're going to have copper ions coming off of the metal there. And in here we're going to have copper ions plating onto the copper metal. So if we want to see what that looks like in terms of our reaction, we're going to have E cell is equal to our E0 cell. Now our E0 cell, remember, is your cell under standard conditions, which we know is 0 volts, minus our constant 0.0592 over 2. We do still have a number of electrons being transferred, and since we're working with copper 2+, that's going to be 2, and log of 0.01 over 2. Now it's 0.01 over 2 because the ion that is in the products here is on the oxidation side, so that's my 0.01 molar, and then the 2 is the concentration of copper ion in the reactant side, and that comes from the side where reduction is occurring, and so that concentration is 2. And we see that we get there a 0.068 volt battery, even though we've got 2 copper electrodes. So this comes as a result of as a difference in voltage. Now another interesting concept in electrochemistry is something that is called electrolysis. Now electrolysis is just the opposite of a galvanic cell, an electrolytic cell. And when we're using a spontaneous galvanic cell, it uses that chemical change to create electrical energy. Now an electrolytic cell does exactly the opposite of that. It uses applied electrical energy in order to create chemical change. And so as a result, this is a non-spontaneous reaction. We are forcing a reaction to go in a direction that we want it to, not necessarily the direction that nature wants it to. And the process of electrolysis is very important in industry. It's one of the ways that we refine metals, so we can take metals that do not normally reduce, something like magnesium, which is a very easily oxidized metal. But if we want to reduce it to get metallic magnesium, we would have to force it to take electrons and become magnesium metal. Also, anytime that you are recharging a battery, you are forcing the galvanic cell to go in reverse, and that's what recharges your battery. And of course, anytime you're recharging a battery, you have to plug it into something and provide a power source to force that reaction to go in reverse. So remember, it's non-spontaneous, and as a result, we have to have a constant applied energy to push it in the reverse direction. So those electrons are forced to go in an opposite direction, and we have to have that applied energy. Now, in an electrolytic cell, we have some differences as far as the not the charges, but the signs on our electrodes. By definition, we still have oxidation occurring at the anode, but because everything is moving in reverse, your anode will now have a positive sign, and your cathode is just the opposite. It will have a negative sign in an electrolytic cell. But we still have oxidation happening at the anode. We still have reduction happening at the cathode. The only difference is that the signs of these two electrodes have changed. Let's take a look at a picture of an electrolytic cell there versus a voltaic cell. So there we have a zinc and copper cell there. We see that when we have zinc and copper working in a voltaic cell, we have a voltage of 1.10 volts up here, and the electrons are moving from the zinc to the copper because that's the way that nature wants to move those electrons. However, if I want to recharge that battery, I've got to make the electrons move the other direction, and so notice that I have to apply a battery rather than just a voltmeter, and I'm using a positive electrode here to attract electrons away from my copper, and negative to supply them down to the zinc. And so we're going to have reduction taking place here at the cathode, but now this is my negative sign, and I'm having oxidation here happening at the anode, but this is now the positive sign because it's hooked to the positive electrode. So what I'm doing here is forcing electrons to go out of the copper and over to the zinc. Notice also that my voltage source here says greater than 1.1 volts. Now the reason for that is that there's a natural driving force pushing those electrons from the zinc to the copper, and that potential is 1.1 volts. So if I want to make them go in reverse, I have to apply a voltage that's greater than 1.1 volts in order to make those electrons go in the opposite direction. It's just like if you have a ball rolling downhill, gravity is applying a certain force to move it downhill, and if you want to push a ball back uphill, you have to overcome that force of gravity, and then if you want to continue to move it, you have to apply a force that's greater than what gravity is trying to pull it down with. If you apply the exact same force, then the ball wouldn't move at all. But if you want to move it back up, you're going to have to not only equal the force of gravity, you're going to have to go greater than the force of gravity to make it move in a direction opposite of what you want. So the same applies here for these electrolytic cells. Now, with a lot of cells that use electrolysis, you've got to be very careful about utilizing aqueous solutions. And the reason we have to be careful is because water is present in aqueous solutions, and water is also very electroactive. It can either be reduced or oxidized, and you can create hydrogen gas and oxygen ions, or oxygen gas and hydrogen ions, depending on which way electrons are flowing. And so you've got to be very careful. Now, generally, the reaction that is more easily oxidized or reduced is what will happen at an electrode in an electrolytic cell, but there are some issues with kinetics and concentrations, and that isn't always the case. And so we always have to be careful about recharging a water-based cell, because if you start making hydrogen and you get a spark, you can get an explosion. This is something that was very common many years ago with recharging car batteries, or trying to jump a car battery. Essentially what you're doing when you jump a car battery is applying an overpotential to try to get that battery to recharge a little bit, and in doing so you can accidentally start to electrolyze the water and start to make hydrogen gas, and again, if you get that spark around that hydrogen gas, you can get an explosion. One of the nice things with electrolysis is that it is actually a very quantitative exercise. It's something that you can measure very well, and it's something that engineers do a lot if they're working in a processing plant where they are depositing metal, actual metal, electrolytically. And we're going to focus on the amount of current and the time that it gets done, and that tells us a charge. So the amount of current passed through the electrolytic cell can be used to calculate how much product you expect. And so we need to look at the amount of charge, C, in coulombs, and we're going to use the current in amps times the time in seconds. And so a coulomb is really just an amp second. Now, once we know how much charge was passed through there, we can use the Faraday's constant to determine how many moles of electrons was used to get that charge. So we have our charge in coulombs times 1 mole of electrons per 96,485 coulombs, and that tells you how many moles of electrons you actually moved in the reverse reaction. And once you know how many moles of electrons you have, you can calculate how many moles of material should have been deposited. So we're going to use those moles of electrons and calculate how much material was deposited. So let's take a look at an example here. And so we've got a current of 2.40 amps. We're passing that through a copper solution. It's got copper 2+, and that 2+ is important because that tells us the electrons. And we're going to pass that through for 30 minutes. And what we want to know is what mass of copper is deposited, and we want that mass in grams. So the first thing we want to do is calculate the amount of charge. And so charge is equal to our current times our time in seconds. Now notice that our time was given to us in minutes, and the coulomb is equal to an amp second. So anytime you're given minutes or hours, you've got to make sure you convert those to seconds. And so we've got 2.4 amps times 1800 seconds, and that gives us 4,320 coulombs of charge was passed through. From there, we can calculate the number of moles of electrons that are involved in that many coulombs. And so we have 4,320 coulombs times 1 mole of electrons per 96,485 coulombs. And when that works out, we get 0.0448 moles of electrons. We can then take this and calculate the moles of copper, and from that the mass of copper. So the mass is going to be equal to the number of moles of electrons times number of moles of copper per moles of electrons times the grams of copper per moles of copper. And if we look at our units here, we can start canceling things out. We're going to have moles of electrons canceling with moles of electrons. I've got to get that one canceled down there. Doesn't want to go on my slide here. And then we're going to have moles of copper canceling with moles of copper, and the only thing that we're left with there is grams. Okay, so we end up with, in our calculation then, 1.42 grams.